All right, the activity of pure solid or liquid is approximately A equals E to the V bar P minus P naught over RT, where V bar is the molar volume. For a pure solid or liquid under typical conditions, the quantity V bar P minus P naught over RT is quite small, primarily because the molar volume is small. And so the activity is approximately 1. So as that approaches 0, the activity is going to be 1, so the smaller it is. Use the following data for liquid water at 300 Kelvin to verify the activity is about 1 over a wide range of pressures. And so, take a look at the data. So we have the pressures here in bar, and then we have what? The density in grams per milliliter here. And so this particular problem, these types of problems, some of these advanced problems, like there's one about the the particular problem like this is kind of similar to this problem. A while back ago, we were talking about specific heat of water, and what did we say? The specific heat of water is 4.18, and we usually use 4.18 over the entire temperature range. But you know, in reality, 4.18 is only valid at what temperature range? Do you know what temperature range that's valid from? It's valid from 4.5 degrees C to 5.5 degrees C. If we're not at 4.5 to 5.5, then the specific heat actually changes, you know, with temperature. And so, I don't know, it was a long time ago when we were talking about thermo. Actually, it wasn't that long, I guess. It seemed like a long time ago. You know, if we really wanted to do this problem correctly, you know, how many joules it requires, then what we have to do is we have to use this kind of equation, you know, the temperature dependent, right, rather than just saying it's 4.18. And so I talked about this equation, the temperature dependent one, and then we looked at the temperature dependent one for water as a review of chapter 7. And so so this is the temperature-dependent specific heat of water. The temperature-dependent specific heat of water is equal to minus 1.0 times 10 to the minus 7 times the temperature cubed plus 1.0 times 10 to the minus 4 temperature squared. So it's a fourth order equation. But, you know, in this, I think in Chem 1A I signed this particular problem, but the purpose of signing it wasn't to do the math. The purpose of this problem was to recognize that, you know, the specific heat does vary, right? And the same thing with this. Well, we just take it as 4.18 because this is too much hassle, too much work to do, correct? Yeah, too much hassle, too much work to do. So that's the exact same purpose why I signed this assignment here in chapter 15. chapter 15, number 97 is it's like similar to that. You know, yes, I'm not going to ask you a question on the test. What is the, like in Chem 1A? In Chem 1A, I wouldn't ask you a question on the test. What is the specific heat of water at 92 degrees Celsius? And then you'd use that particular equation. Well, the same thing here. I'm not going to ask you to calculate the activity of water, pure liquid, at, let's say, under these conditions or under those conditions, right? Well, what this is saying is that, you know, what we do is we just assume the activity of pure liquids and pure solids is 1. And so what you can do in this style of problem, this style of problem is not just taking the numbers and plugging in, because we got to calculate the molar volume. Molar volume is going to be moles per liter, which, so we're going to have to convert that from grams per milliliter to moles per liter, which is just dimensional analysis. And then just plug that in. It's not to plug in the numbers and see if you could do the calculation and tell me what the activity is at a specific temperature. It's just to get an idea, a gauge that, yeah, the specific heat doesn't vary that much. You know, if we were actually to plug it into that equation, and to 3 sig figs is probably good. We're good, you know, to 3 sig figs over a pretty wide range. And the same thing with this. You know, you look in the solutions manual, how much did it vary? Because I assume everybody can just take the numbers and just plug it in there, that kind of thing. And so the purpose of this question was not to necessarily do the calculation, but what the purpose was is to see how much did the activity actually vary, you know, in this range. And you could do that by just plugging in some numbers there, or you could do that by looking at the solutions guide for this particular problem. And so, so that being the case, you know, you guys, like I said, the way I approach homework may be a little different than, the way I approach homework is definitely different than the way I was taught to approach homework. I was taught to approach homework was you don't look at the solutions guide. What you do is you pound your head against the wall until it sinks in, and then check your answer with the solutions guide. Okay? That's the way. And so don't worry about this one so much, because the purpose was, you aren't going to see this on a test necessarily like this, but it's just to give you an idea, because sometimes we say, okay, the activity's 1, you know, and people take that as, you know, not just a rule, but, you know, maybe not just a law, but, you know, whatever. All right, was that it, this one, or was it the math?
No, it was the math, like I didn't know what.
Oh, okay. The math is then, you know, molar volume, this would be back in chapter, whatever. But molar volume, the first time molar volume is introduced is in chapter 6. But it's for gases, but the same exact thing. You could do the molar volume for anything. And we have molar volume for, actually, no, the first time it was introduced was in chapter 2? It was either chapter 2 and then 6 and then again in 9, because there's one, in periodic trends, there's one trend where you plot the melting point versus the molar volume. I don't know if you know, it's just one of those things at the very end of the chapter. It's not that important. But molar volume is just moles per liter. So grams, you know, this is water, so 18.02 grams per mole. And so if you want to do the calculation, you can just do this. You take this and convert from grams to moles by 18.02 divided by 18.02 grams per mole. And then convert from milliliters to liters, a liter per 1,000 milliliters, and that will be the molar volume there. And then plug those in over there. Now, P naught, you know, P naught, P minus P naught. You know what P naught is? Usually. P minus P naught. What is P naught?
1 bar.
Yeah. P naught is usually your standard, and the standard pressure is 1 bar, and so P naught would be 1 bar in this case. You know, if P is 1 bar and P naught is 1 bar, then 0, and the activity would be 1. Okay. If the pressure is not, then it's going to change. Okay, other questions? Speaking of chapter 15, I had a request from the morning class. You know, they're saying that they usually have their study group on Wednesday, so they requested if it was possible to move the exam to Thursday. And since there weren't any objections in the morning class, so they said, okay, we'll move it to Thursday. What do you guys think? Are there objections to moving it to Thursday, or no? All right, so we'll just move the exam till Thursday. And then, that's it. Maybe I'll post something. If you do have objections, let me know, because if you have multiple exams on Thursday, I can see why you want that difference. Well, let me know. All right.
I can do 2016.
26. Okay, number 26. At 2000 Kelvin, Kc is 0.154 for the reaction. 2 methanes goes to, you know what C2H2 is? C2H2 is acetylene, or ethine. It has a carbon-carbon triple bond, plus 3 hydrogens. If a 1.00 liter equilibrium mixture at 2000 Kelvin contains 0.10 moles each of methane and hydrogen, what is the mole fraction of C2H2 present? So, the reaction is 2 methanes goes to C2H2 plus hydrogen, 3 hydrogens. This mixture is at equilibrium. So 1.00 liter equilibrium mixture. So this equilibrium contains 0.10 moles each of methane. So it's 0.10 moles divided by 1 liter, so it's 0.10 molar. And then the hydrogens can be 0.10 molar. And that means we're going to have some acetylene at equilibrium, but they didn't tell us. They didn't tell us how much acetylene we have, but you know, we should be able to figure that out because there's only one unknown in this particular case. And so we got Kc. Kc is equal to 0.154, and this is going to equal the acetylene concentration times the hydrogen concentration cubed divided by the methane concentration squared. So just plug in the numbers here. Actually, let's just solve for the acetylene concentration. We solve for the acetylene concentration at equilibrium. That's going to be Kc times the methane concentration squared divided by the hydrogen concentration cubed. So let's just plug in the numbers here and see the acetylene comes out. And so Kc is 0.154. The methane concentration is 0.10 squared. And so times 0.1 squared divided by the hydrogen concentration cubed divided by 0.1 cubed. I guess I didn't have to do that much. I just simplified it. And so the methane concentration comes out to 1.54 molar. We should do a double check just to make sure. So this comes out to 1.54 molar. Does it work out? And so let's go ahead and take this. It's going to work out because I just did it. unless I made a simple mistake. 0.1 cubed times 1.54 divided by 0.1. It gives me oops, I guess I did screw it up. Let me try that one more time. I didn't get the right K C value here, so I'll try it again. 0.1 cubed equals divided times 1.54 divided by 0.1 squared. Oh, okay, it checks out. And so this is the equilibrium mixture here. It's 1.1 molar, 1.5 molar, and 0.1 molar. That's the equilibrium mixture. Well, they don't want the equilibrium mixture, they want the mole fraction. Now, mole fraction, this is back in chapter 6, is where mole fraction was first introduced. The mole fraction is the moles of A over the moles total. If you recall from chapter 6, the mole fraction is also equal to the pressure fraction, which is also equal to the volume fraction for gases. And so, well, they're just asking for the mole fraction. So, well, the moles of A is 1.54. Now, what is the total moles? The total moles, if I have 1 liter, will be 1.64, 1.74. So the total moles will be 1.74 times 100. Well, actually, they just want the mole fraction, sorry. They don't want the mole percent. If I did the mole percent, I'd have to times it by 100. But since they just want the fraction, I'm just going to leave it 1.5 or 1.54 divided by 1.74, and that gives me a mole fraction of 0.885. And so the actual fraction is 0.885 moles of acetylene for every 1 mole of everything total. So that's a mole fraction. If the conversion of methane to acetylene is a conversion favored at low or high pressures? Low or high pressures? Yeah, well, what we got to think is this. Yeah, high pressures will shift it to the left. Low pressures should shift it to the right. You know, the low pressure is going to favor the side with more moles of gas. We got 4 moles of gas on the right, 2 moles of gas. And so as a conversion, it's going to be favored at low pressures. C, if the equilibrium mixture at 2000 Kelvin is transferred from 1.0 liter flask to 2.0 liter flask, will the number of moles of acetylene increase, decrease, or remain unchanged? And so this is the same thing. If we increase the volume, which side is favored? The side with more moles of gas or the side with fewer moles of gas? Increasing volume is going to favor the products. So that's going to increase the amount of acetylene. So this is Le Chatelier's principle. Increasing volume is also going to decrease the pressure of everything. And so that would be number 26. Any other questions on chapter 15? All right, let's go. I'm going to talk just a little bit about chapter 16. I'm not totally done with chapter 16, and then I have to jump to chapter 17 because chapter 17 is the topic of today's lab. Today's lab is buffers. Let's look at that. So let me finish the problem we were doing yesterday, H2SO4. We had 0.10 molar. H2SO4 is diprotic acid. And so if we have diprotic acid, then there's going to be a Ka1, a Ka2, and a Kw. We're going to have 3 steps contributing to the hydronium. As you recall, simultaneous is horrendous. It's difficult. And so what we try to do is we try to do every problem stepwise. Stepwise is not correct, actually. What's correct is to solve all equilibria, multiple equilibria simultaneously. But since the math is too difficult, we just try to solve it stepwise and hope that it's good enough. If not, then we should recognize that it's not good enough. And so here we'll do step 1. Step 1 is going to be the largest K value. We just go in sequence. So the largest K value is going to be K1. Did you guys finish this already, this problem, or still working on it? Or was this the problem we left off with last time? Was it H2SO4 or was it the other one? This was H, okay. All right, this is going to go to hydronium plus HSO4 minus. This is Ka1. Everybody should know what Ka1 for sulfuric acid is. What is it? Very large. Oh, very large means is we just assume 100% reaction. And so initially we just reset everything to the left. We assume nothing's happened and then let it change. So re-equilibrate. So reset to the left, let it equilibrate. When we let it equilibrate here, we're going to lose how much? We're going to lose all of it. So this is minus 0.10 molar. So we know what X is. This is plus 0.10 molar plus 0.10 molar. And so at equilibrium, we expect 0 molar H2SO4, 0.10 molar hydronium, and 0.10 molar HSO4 minus. Now, normally, there are 2 types of problems you're going to encounter in Chapter 16. One is what is the pH? 2 is what is the inventory? If we were just interested in pH, then step 1 usually supplies the bulk of the hydronium or the bulk of the hydroxide, if it's a base. And if we're interested in pH, typically we ignore the step 2, step 3, etc., unless we have a condition where step 2 has kind of a big K. And so let's take a look at step 2. Step 2 would be, well, sulfuric acid is diprotic acid. And so here, HSO4 minus can hydrolyze water to form hydronium and sulfate. And so let's look at the Ka2 value for this. The Ka2 value is 0.011. In other words, it's 1.1 times 10 to the minus 2. Is 1.1 times 10 to the minus 2 kind of on the big side or the small side of weak acids? It's on the big side. Since the K value is kind of big, then I got to worry about it. If the K value were pretty small, let's say the K value were like 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, I wouldn't worry about it for pH. But this is kind of big, so here we're going to drop this down here. And so I create 0.10 molar HSO4 minus from step 1. And, oops, that's this. And then I have to be aware of this. I have common ion here, and common ion is going to really change the amount of reaction I have here, hydrolysis, because if I have a lot of product there to begin with, I'm not going to get as much hydrolysis after that. And so I have to really make sure that the common ion is carried through as well. And so we have 2 common ions, the HSO4 minus and the hydronium. So this has got to go to the right because we got 0 molar sulfate, so this is going to be minus X molar plus X molar plus X molar. And so at equilibrium, we're going to have 0.10 minus X, 0.10 plus X, and X molar. Now, Ka2, this is going to equal the hydronium ion concentration times the sulfate ion concentration divided by the HSO4 minus concentration. And so let's go ahead and plug that in up here. So 0.011 is equal to the hydronium ion concentration, which is 0.10 plus X times X divided by 0.10 minus X. And so what we're going to do is we'll just do the simplifying assumption. The simplifying assumption says if we add a drop of water or if we lose a drop of water, it's not really going to change this by much. So 0.10 plus a drop is nothing. It's just 0.10, and 0.10 minus a drop is just the same thing, 0.10. So this is x. And so we get this situation where x is equal to Ka2. Some people make a big deal out of that. X is only equal to Ka2 if the simplifying assumption is successful. So x is going to be 0.011 here. Was the simplifying assumption successful in this case? Well, if I look at the initial, we'll call the initial 0.100, and this is 0.011. So 0.100, 0.011 means that the percent change is 11%. 11% change is not valid, and so the simplifying assumption failed, and therefore x is not. If the simplifying assumption works, then x is equal to Ka2. If it failed, it's not. And so unfortunately we have to use the quadratic for this one. And so let's go ahead and do that. I'm going to try to get this into quadratic form. So 0.1 times 0.011 should give us 0.0011. 0.011 times x is going to be minus 0.011x is equal to 0.10x plus x squared. And then let's rearrange this into quadratic form. This gives me x squared. Let's add a 0.011, so this is going to be plus 0.111x. 0.111x minus 0.0011 is equal to 0. All right, can somebody with a calculator help me out here? We'll just plug in the ABC. Oh, you got it? Okay. X equals 0.915. Thanks. All right, when we made the simplifying assumption, we came up with 11% change. It really isn't 11%. It's only about 9%, because we started off with 0.100. And so this is about a 9% change here. In fact, this is why the first proton comes off 100%. The second proton, only 9% of the second proton comes off. You know, the remaining 91% stays on. And so this is going to be 0.1 minus 0.00915 gives me 0.09015, or 85, sorry. 0.85. So it's about 91% unreacted here. And then over here, the hydronium, I'm going to get about 9%, 10% more hydronium. So if I go 0.10, this is the amount of hydronium I got from step 1. And then I'm going to add to it the amount of hydronium I have from step 2. I'm going to get 0.10915 molar. And so that's about 0.11. And so, yeah, it contributed. Step 1 generated 0.10, and step 2 I get 0.11. And then the sulfate's going to be 0.00915 molar. Here. All right, now I want to double check step 2 to make sure I didn't make any simple errors here. 0.00915 times 0.10915 equals, divided by 0.09085. And that comes out to, my K on the double check, comes out to 0.01099. It's supposed to be 0.011. I got 0.01099. Close enough? Yeah, that's close enough. So that's good. But I have to worry about this. Now, I added a significant amount of hydronium, so what's going to happen is this. The hydronium is going to increase, and then it looks like the bisulfate decrease. And so you might say, oh, those are going to cancel each other out, still stay in equilibrium. But essentially what happens is step 2 is going to perturb step 1. Correct? Do I have to worry about it? Yeah, for sure step 2 perturbs step 1 because now all these concentrations have changed, but I don't have to worry about it because step 1 is a strong acid. Strong acids are just one way, so strong acids and strong bases aren't going to be affected by the Chatelier's principle. And so we're okay. Now, here, I look, do you think step 3 would contribute some significant hydronium to this? And so it looks like step 3 will give us a little bit more hydronium. But when I look at the K value for this, Kw is equal to 1.0 times 10 to the minus 14. With a K value this small, do you expect much additional hydronium? No. And so in fact, if I was interested in pH, I'd try to stop at the first step, unless the second step has kind of a big K, which this one did, and then I do it. But when I look at the third step has such a small K, I don't expect much of anything extra. So if I was only interested in pH, I would have stopped here at step 2. If I'm interested in inventory, I'll have to take this all the way to the end. And so I'm interested in inventory here, so we'll do that. H2O is pure liquid. And so what we have here is a common ion. We're going to have this common ion. Hydronium is going to be a common ion in all 3 equilibria. And so the hydronium is going to go here at 0.10915. And the hydroxide, we're going to assume nothing's happened. You know, all the water molecules have been reset to the left. And now we're going to let it react. And so we're going to get a little bit more hydronium from here. Now, how much is a little bit more? How much is a little bit more is this. If there was no common ion here, if this was 0 and 0, then how much hydronium would I get? If both of these were 0 and 0 initially, then I'd get 10 to the minus 7, right? I'm going to get less than 10 to the minus 7 because I have common ion here. And so the most I'm going to get as x will be 10 to the minus 7, but I can't even get that because of the hydronium already present. And so when I'm thinking about how much additional hydronium I'm going to get like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar maybe? Will 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 have any impact on this? No, because that's like 7 zeros, 8 zeros, 9 zeros before the first number. That's not going to have any impact there. And so here, I can already tell the pH will not be changed by the additional hydronium we get in step 3. But for sure, hydroxide is important. Hydroxide is significant here. And so let's go ahead and calculate this. This is going to be 0.10915 plus x times x. So it would be the hydronium times the hydroxide. Here, I'm going to try the simplifying assumption. So we try the simplifying assumption. This is 10915, like plus a drop of water. This would be about the same times x here. And that gives us an x equal to so 1 times 10 to the minus 14 divided by 0.10915. And so I get 9.16 times 10 to the minus 14. Now let's figure out the percent change here to justify the simplifying assumption. And so the percent change, I'm going to just do orders of magnitude because the change is so small. The change is 10 to the minus 14. My initial is 10 to the minus 1. And so it's about 10 to the minus 14, maybe 10 to the minus 13, divided by 10 to the minus 1 times 10 squared percent. And so 10, that gives us 10 to the minus 12, 10 to the minus 11. So this is about 10 to the minus 11% change. That's way less than 5%. So in fact, you know, if you use the quadratic here, you wouldn't get a better number at all. And so this comes out to 0.10915 plus, well, how much additional hydronium am I going to get here? I have 13 zeros. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 916. So I have to add some more zeros here. 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. 9 zeros, 10 zeros. And so 0.10915 and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then a 916 molar. And so did I add much? This is how much additional hydronium I added in step 3. Nothing, really. But hydroxide, it is significant because hydroxide we started off with nothing. And so if we start off with nothing, then 9.16 times 10 to the minus 14 is something. That's significant. We can't ignore that here. But as far as the pH goes, if we stopped at step 1, we would have gotten a pH of 1.00. That's wrong. If we stopped at step 2 or step 3, my calculator can't even handle that many digits. So let's see what the pH comes out to. So just do the negative log of 0.10915. And so the pH I get is 0.961. And so step 2 was a significant contributor. Step 2 dropped the pH from 1 down to 0.916. And so what we'll do with the inventory is we're going to just keep a track of the running totals here. So if I'm interested in the species present in a beaker that's labeled 0.10 molar H2SO4, what am I going to find in this beaker? Well, will I find any H2SO4 molecules? And according to this, with a very large K, I'm going to find none. So this should be 0 molar here. All the molecules should have hydrolyzed. And so this is the end of the road for the H2SO4. And then I go to the hydronium here. The hydronium, we have a running total. So 0.1 from step 1, and an additional 0.01 from step 2, plus an additional minuscule amount from step 3. And so that gives us 0.109 molar hydronium. So the hydronium is just a hair above 0.109 molar, or 0.11 molar, rounded to the correct number of gigs. And so this would be the total. Now, this hydronium must satisfy the equilibrium for all the equilibria because this is a common ion. And so we see, does it satisfy this one? Well, actually, we didn't double check. I didn't double check this. So let me double check this just to make sure that's the right number here. And so I'm going to go with a 0.10915, 0.10915 times 9.16 times 10 to the minus 14. 9.16 times 10 to the negative 14. And so I didn't carry out all the digits. But I got a K of 0.9998 times 10 to the minus 14. Is that pretty good? Yeah, that's good. So we're good there. This hydronium has to satisfy all 3 steps simultaneously. Does it? Yes, it does. Okay, so that's the total hydronium. Okay, then we have the HSO4 minus. The HSO4 minus, it goes down to here. Ooh. This is the end of the line for the HSO4 minus. And so when I look at the HSO4 minus, it's 0.09085. But I have a problem here because it doesn't, it's not the same as step 1. And so the HSO4 minus concentration changed, and so it doesn't seem as if it's going to satisfy both equilibria, this one concentration. I can't have 2 separate concentrations, can I? But we know something, and what do we know about this?
First one is in equilibrium.
Yeah, first one has a K very large. We don't have to satisfy this. I mean, we could change it, and it's going to have no impact. And so that's okay. The final concentration of the HSO4 minus is this. And it doesn't appear in that one, so we're safe. Okay, then the sulfate. The sulfate ends here. So we're going to have some sulfate in the solution. Sulfate is going to be 0.00915. And then the only thing left will be the hydroxide. It's here. And the hydroxide concentration will be 9.16 times 10 to the minus 14 molar. And so an acid solution, which this is an acid solution, has to have a hydronium concentration greater than the hydroxide. And in this case, it has a huge hydronium concentration. The only place the hydroxide comes from are the collisions of water molecules, autoionization of water. All right, so this is kind of the standard type of problem. What else we're going to see in chapter 16 are problems like this. Actually, I wasn't supposed to erase this just yet. Leave it out. But other examples, in this case, you know, we had multiple contributors to hydronium. How many contributors to hydronium did we have? 3, right? K1, K2, K3. Well, sometimes what we have are acid mixtures and base mixtures. And so when we have acid mixtures, then we can have different acid mixtures, which would be like this. HCl and HI. HCl and HI, if I have, let's say, 0.10 molar HCl and 0.10 molar HI, then I have a mixture. But the way we handle this is the same as any other. We just look at all the hydronium ion contributors. And so which one do we start off with first? Well, we have HCl and HI. Which one has a larger Ka? HI, even though HI has a larger Ka, both of these go to completion, so it doesn't matter which one we do. Now, if I pick this as step 1 and this is step 2 or vice versa, then step 2 is definitely going to impact the amount of hydronium I create, right? But that's not going to have any impact because both of these are strong acids. And so we look at the Ka for this one, the Ka for this one, and Kw. Those would be my 3 hydronium contributors, and I do it stepwise. Just add it up, you know, as we go along. The same thing, we could have base mixtures. That would be similar, like strong base, strong base. But let's continue. I could have an acid mixture like this. I could have a strong acid and a weak acid. So the strong acid would be HCl, the weak acid would be acetic acid. And so all I do is I look for, if I have a mixture of acids like this, I just do the biggest K. The biggest K would be HCl. That would be my step 1. Step 2, I'd compare. I have a choice. I could do Ka for acetic acid or Kw. Which one's bigger, Ka for acetic acid or Kw? Acetic acid. And so what would happen here is this would be my step 1, strong acid. This would be my step 2, the weak acid. The weak acid is going to contribute some hydronium. The only issue is there's going to be a common ion effect, right? The common ion effect is going to impact how much hydronium we get from acetic acid. It's going to be a little less. And the same thing, we're going to have common ion effect for Kw here. And so just like what we did for H2SO4, you know, most of the acid is going to be produced by this, most of the hydronium, and then a little bit from the acidic, and probably not much from Kw. And so we could have like a whole bunch of acids, you know. We could have HCl, acetic, which we'll abbreviate HAC, and we could have others like HF. And we would just do this stepwise and just pretty much have a running total of hydronium from all the hydronium ion producers. All right, in chapter 16, it's just going to be acid and water, you know, or base and water. And so base mixtures are going to follow the same kind of pattern. Maybe we'll look at some base mixture and acid mixture problems later. But for right now, I'm going to skip it. chapter 17 is more of the same, except it gets a little bit more, the mixtures get a little bit more varied, because if you think about this, you know, these acid mixtures are actually acid-base mixtures. The acid is HCl. Do you know what the base is? Well, A means acid hydrolysis. Hydrolysis is with water. And so these are actually acid-base mixtures. It's HCl plus the base water, it's HI plus the base water, and it's H2O plus the base water. And so all these acid mixtures are just, you know, looking at the acid plus water, hydrolysis. The same thing with the base mixtures. All the base mixtures are going to be base and water. In this case, water would be the acid. Okay, now what we're going to do when we go to chapter 17 is we're going to look at a whole bunch of different acid-base mixtures. So chapter 16 is looking at acid-base mixtures. In acid-base mixtures, we kind of follow the same pattern. The acid-base mixtures is we take the strongest acid and react it with the strongest base present. Strongest acid plus the strongest base present. And so here, let's look at some examples of this. And so, like I said, we're going to have some more complicated So an example here might be, let's say, HCl and sodium chloride. If I have HCl and sodium chloride, what do I do with this mixture? Well, this mixture, I'm going to just take the strongest acid present. What's the strongest acid? HCl. And then take it and react it with the strongest base. Well, sodium chloride consists of the sodium ion and the chloride ion. Chloride ion is a base. Is it the strongest base present? Is chloride the strongest base present? What do you know about chloride? Extremely weak. It's too weak to even be considered a base. Therefore, the strongest base that's present is H2O, liquid. And so if this were 0.1 molar and 0.10 molar, then the strongest acid is HCl, the strongest base is H2O, and I'm going to form hydronium and chloride. Now, all I do is I just set up my ice chart. So here, I know I have 0.10 molar HCl, right? Water is 0. I assume nothing's happened yet, so the hydronium is going to be 0. But I have to be careful here, because do I write 0 for chloride? No, I don't write 0 for chloride because I have some chloride here. This is what we call a common ion type mixture. Common ion type mixture is, well, the sodium chloride has a common ion with HCl. That common ion is chloride, and so this is 0.10 molar chloride. But unlike other common ions, you know, this one is not going to be affected by the common ion. HCl is not impacted. Like I said before, other things are impacted. For example, if I have some common ion here, typically we don't make as much. And so if there's a change, that change is going to be smaller than what it normally is. But for HCl, it's a different story, because HCl is a strong acid. Strong acids have a very large Ka. And so this is going to have no impact at all. Even though I have that common ion there, I still say this is going to ionize 100%. And so this is going to be minus 0.10 molar, plus 0.10 molar, and plus 0.10 molar. So it's different. And so this is going to be 0, and this is going to be 0.10, and this is going to be 0.20 molar chloride. So that's good. All right, what if I have some other scenarios? So let's look at some of the scenarios that we're going to have in this chapter. And we're going to try to figure these out. And so I might take a strong acid. So the next example I'm going to look at is strong acid HCl. And this time, let's react it with a strong base, like sodium hydroxide. So if I take HCl and sodium hydroxide, the strongest acid present, HCl, strongest base present, sodium hydroxide, I'm going to form salt, sodium chloride, and water, H2O liquid. What's the K for this? Is this a Ka? No, this is not a Ka because Ka is acid plus water. This is a Kb? No, it's not a Kb because Kb is base plus water. This is just K, and we call this K of neutralization. And so what is the K value for this equal to? So we look in Appendix D. It's not in Appendix D. Nowhere to be found. But you should be able to figure it out. The way you can figure it out is think about this. This is strong acid plus a strong base. This is strong acid plus a weak base. Sodium acetate, acetate's a weak base. And so this is going to form acetic acid, which is a much weaker acid than HCl and sodium chloride. This is the driving force for this is the driving force for this. And then we have HCl plus H2O liquid. How strong of a base is H2O liquid? Not very. And so do you know what K is for this bottom reaction? What is the K value for the bottom reaction? Yeah. K is very large for the bottom. We know that because that's the Ka reaction, or the Ka value. But this is not a Ka reaction. Ka is just the acid plus water, water being the base. This is an acid plus base reaction. This is not Ka, but we should know it. What is it?
Very large.
Okay. We would say it's very large, but I'm going to say it's very, very large. Why? I'm going to say it's very, very large because let's compare the base strength. Which is a better base, sodium acetate or water? Sodium acetate's a much better base. And if that's the case, there's going to be a bigger driving force for this. To show that there's a very bigger driving force, I'll just say very, very large. And the top one, what's the top one going to be? Top one's going to be very, very, very large. And we do these, you know, these top two are what we do in Chem 1A. In Chem 1A, you assume 100% reaction, right? In complete neutralization for this. And so you've done strong acid, weak base, and strong base, weak acid, that type of stuff. This is Chem 1A and Chem 1B. And so the same thing goes, you know, for strong base. If I take a strong base, sodium hydroxide, and a strong acid, HCl, then that's one thing. I can take sodium hydroxide as strong base and a weaker acid. What's a weaker acid? Let's do something like ammonium chloride. Ammonium chloride's a weaker acid. Or I could do sodium hydroxide plus an even weaker acid. An even weaker acid would be H2O liquid. And I know the K's for these. What are the K's? The bottom one's called Kb. Kb for a strong base is very large. And then this middle one will be very, very, and the top one will be, yeah, very, very, very large. And so we have those. And so those aren't that bad because those are, we could actually do those using Chem 1A stoichiometry, or we could do those using Chem 1B stoichiometry using an ice table rather than factoring those in. But what happens when we have something like this? What happens if we have a weak acid and a weak base? A weak acid and a weak base. Let's give me a weak acid. All right, let's go with acetic acid. Give me a weak base. Probably one of the most common weak bases is ammonia. So we'll go with acetic acid and ammonia. A common weak acid and common weak base. So acetic acid plus ammonia, this is an acid-base neutralization reaction. And so acetic acid plus ammonia is going to make what? Acetate and ammonium. Acetate and ammonium. What is K for this?
Very small.
K is going to be, yeah, much smaller than very large. But, you know, I want a number. I don't want very small, meaning no reaction. Right? There should be some sort of reaction, even though it's not, I don't know, are we going? Yeah, we're going from stronger to weaker, so this is favored. You know, acetic acid is a stronger acid than ammonium, so this is a driving force for this. But we wouldn't call it very large, would we? No. And so I want a number for this. So how can I get a number? Tell me all the ways I can determine K. Appendix D? Unfortunately, this one's not an Appendix D. This one's not. But I could use Appendix D data. How can I figure out what K is from Appendix D data?
Using the Hess's law?
Well, I could use it, yeah, using Hess's law I could do it. And so that's one way. I could try Hess's law. Or I could use thermodynamic data, you know. And because K at 298 Kelvin, K is equal to minus delta G over RT. So I could figure out what delta G is from Appendix D and then get my K value. Or if I don't want to do it thermodynamically, I'll use Hess's law. Hess's law type calculation where I can add up equations and figure it out. And so what equations can I add up? What type of equations are in Appendix D? So let's take a look at Appendix D really quick. KAs. KAs are in Appendix D. And so I have a KA like this. And so let's look up the Ka value. Well, what is the Ka equation? Ka equation would be acetic acid plus what? Water. Here it is, 1.8 times 10 to the minus 5. So I know this one, acetic acid plus water is going to produce hydronium plus acetate. And so the K for this is 1.8 times 10 to the minus 5. And then I need the Kb for ammonia. But you know, normally I'd have to calculate the Kb from the Ka for its conjugate acid. But have you looked at this table? I actually have a table of KBs here. But when I look at the table of KBs, something's strange about all these bases. I have ammonia here. That's good because that's the KB I want. The KB I want is ammonia. And ammonia has a KB, and so KB is base plus water. Base plus water yields what? And so ammonia plus water gives me ammonium and hydroxide. Ammonium and hydroxide. Kb for this is 1.8 times 10 to the minus 5. Well, wasn't that the Ka? Yeah, that was the Ka. These are equal, you know, just by coincidence. If we want more sig figs, they wouldn't be equal. And so there's no connection. It's just so happened to be equal to 2 sig figs. But when you look at all these bases, what's special about all these bases? And so this is a KB table. I told you we can't use the KB table because we have to convert it from Ka. Remember converting? Kb equals Kw over Ka for the conjugate? But we do have a KB table, but there's one restriction about this KB table. This KB table is limited to nitrogen, not just nitrogen, but look at the names. Aniline, codeine, diethylamine, dimethylamine, ethylamine, hydrazine, hydroxylamine, isoquinoline, methylamine, morphine, piperidine, pyridine. What's special about this? They're all amines. Do you guys recall what the amines are? The amines are ammonia derivatives. All those are ammonia derivatives. Ammonia is a weak base. And there are a whole bunch of organic compounds that are weakly basic. Like, for example, a lot of those drugs, codeine, etc. And the only difference is rather than having a hydrogen, we have a carbon attached to the nitrogen. And so if we have a carbon here, it turns out that carbon and hydrogen don't have that big of an electronegativity difference. Carbon's at 2.5, hydrogen's at 2.1. That means the delta minus on nitrogen doesn't change much, And so we still have negative charge density on nitrogen, making this nitrogen pretty basic. Right? Remember about localized negative charge versus delocalized negative charge, What makes a good base is that negative charge. Well, we're going to maintain that negative charge even if we put a carbon there because it's not going to change things by much, right? And so let me ask you this to see how well you understand this. This is called methylamine, where we replace a hydrogen with what we call a methyl group. This is a methyl group. Just takes right there. And so comparing methylamine with ammonia, which one should be a stronger base? Methylamine or ammonia? Well, I'll tell you, they're going to be about the same. Don't look at the chart, yeah. But which one do you predict to be stronger just based on your structural analysis of these two compounds? You expect methylamine to be stronger? How come? Which should be stronger and why? Well, do you remember the inductive effect? What was the inductive effect? The inductive effect was kind of the withdrawing of the electron cloud by a more electronegative atom. Remember that? And so this morning what somebody said was that this should be stronger. The reason this should be stronger is because carbon's more electronegative, just slightly more electronegative, 2.5 versus 2.1. Since carbon's a little more electronegative, it's going to suck some of the electron cloud density away from nitrogen, lowering the delta minus here. In other words, kind of delocalizing that negative charge. Versus hydrogen. Hydrogen's less electronegative. Nitrogen's going to suck all the electron density away from hydrogen, right? Does that sound reasonable to you? So we would say maybe this is going to be weaker because carbon is more electronegative. The inductive effect is going to suck some electron density away from nitrogen. This will be stronger because all that electron density can concentrate on the nitrogen. And when it seeks out protons, the more negative it is, the better. If this is more negative, it's going to be better, right? Okay, so so a lot of people say it's because of electronegativity. That's always the good answer, right? Electronegativity. That was good. And so let's take a look at the data. The data shows ammonia is 10 to the minus 5. And if we go to methylamine is 10 to the minus 4. And so which one is a stronger base? 10 to the minus 5 versus 10 to the minus 4? 10 to the minus 4. In fact, if we look at the numbers here, it looks like methylamine is more than 10 times stronger. And so why is this more than 10 times stronger of a base than this? They're both kind of comparable, 10 to the minus 4, 10 to the minus 5. But why is methylamine more than 10 times stronger?
Because of the bonds.
Because of what?
The bonds
Because of the bond?
Yeah, because of the auto group.
Both of these are polar covalent bonds. Because of what?
The auto group, there's the carbon that's it's actually more dense.
More dense? In what way?
Charge density.
The charge density on carbon?
Actually, on CH3. Not as symmetrical.
Not as symmetrical. This is very symmetric here. No, because if you only use electronegativities and only the Pauling's electronegativities at that, you're using an oversimplistic approach to structure and structural analysis. When I look at this, I don't look at it that way at all. When I look at this structure, I see something totally different. To me, when I look at a methyl group, you know what I see? When I see a methyl group, I don't see a more electronegative carbon than a hydrogen here. I see something else entirely. When I look at a methyl group, I see, and I see something. I see, when I look at a methyl group, I see electron rich. Why do I see electron rich when I look at a methyl group? Well, because methane, methane is a good electron rich fuel. Methyl is kind of similar. But when I look at methyl, I see electron rich, and I go, oh, that's electron rich. Right? Why? And its formal charge is 0. Why do I see electron rich? Oh, because the oxidation state. What's the oxidation state on carbon? What's the oxidation state on carbon? Nitrogen is more electronegative. So you got it, Eric? -2 is correct.
How do you tell the oxidation state?
How did you tell? Can you explain?
Just count the winner takes all for oxidation state bond, using the bonds to electrons.
Okay.
Relative balance.
So who won, carbon or hydrogen? Who wins?
Carbon.
Carbon versus nitrogen. So it's 6. 2, 4, 6. It's supposed to have 4. Got 2 extra.
Cool.
So what I see when I look at this is I don't see electronegativities. I see electron rich. And in fact, actually, this I'm going to introduce some more organic jargon to this class because one of the comments from organic people are too weak in acids and bases and structure when they get to organic chemistry. And so what we call this group here is hydrocarbon, this is called a substituent in organic chemistry. Hydrocarbon substituents like this are electron pushers. They're rich. They got lots of electron density. They can push the electron density to nitrogen. If these are electron pusher, that's going to donate a lot of electron cloud density to nitrogen, making this nitrogen even more electron rich, which makes it even more basic. Right? And I get away from thinking about electronegativities because, what if I put an electron poor substituent? I'm going to put an electron poor substituent on that like this. Hey, this is a nitrogen to carbon, right? And so isn't carbon's electronegativity 2.5? Right? Didn't we say that? Carbon's electronegativity is 2.5. Carbon's electronegativity is 2.5. And so when I look at the bond polarity is about the same here. So electron cloud density distribution is about the same here. But no, I don't see that. When I look at this substituent, I automatically think, wow, that's really electron poor. Electron poor. Why is that electron poor? Well, what's the oxidation state on carbon here? Let's see. Yeah, the oxidation state on this carbon is +4. Now, is this carbon so rich in electron density it can give electron density away? No, this carbon is starving for electron density. In fact, this carbon doesn't have any electron density to give away because it's in the +4 oxidation state. And so what impact that's going to have is when there's a tug of war for electron density between carbon and nitrogen, this carbon's been like a starving a dog as far as in this fight for electron density. So anyway, this is a totally different carbon than this. In fact, this type of substitution, we call this one is an electron withdrawing or electron sucking group. And in organic chemistry, this charge density is very important. We can have electron pushing groups and electron withdrawing groups. In fact, this one, would we expect this to be very basic? No. This one is going to be a heck of a lot weaker than this one. In fact, in amines, a compound like this is not considered an amine. Even though it looks like ammonia, this one is not a base. That's not a base. Why? Oh my gosh, it looks awfully like this. Aren't they the same? They both have the trigonal pyramidal structure. Both of them have this lone pair. Both of them can donate the lone pair. Both of them can accept a proton. But the left one here is an amine. The right one is not an amine. We don't classify this one as amine. The left one has what's the oxidation state of nitrogen on the left? The oxidation state on the nitrogen on the left is -3, -3, -3, +3. So we're going from a -3 nitrogen to a +3 nitrogen. Do you think +3 nitrogen is going to be happy to donate electron cloud density? No, this is not an amine here. And so all these are amines here. And all of them, some are going to be stronger, some are going to be weaker. This is an especially weak amine here. This is a pretty weak amine here too. The reasons for that. And some of them are going to be stronger. So you can see that, okay, we put a methylamine, comes out to 10 to the -4. We go to dimethylamine, it's a little bit more basic, not that much, 4.2 to 5.9. And then we're actually going to see this when we go into lab. We have a acid-base strength lab. And then we go to trimethylamine. And so it goes 4.2 to 5.9 to 6.3. I guess a little bit more basic, not hugely. All right, so let's go back to this. Actually, accidentally erased this. So if we add these two up, then I have my acetic acid, I have my ammonia, I have my acetate, and I have my ammonium. So I'm almost there. I just have two waters, a hydronium and a hydroxide to get rid of. Have you seen two waters, a hydronium and a hydroxide before? Yes. Two waters going to hydronium and hydroxide is called KW. And so here, I have two waters here, I've got to get rid of those. So what I'm going to do is I'm going to reverse KW. So I'm going to take a hydronium and a hydroxide and form two waters. And that gives me H2O liquid plus H2O liquid. If I reverse the equation, what do I do to K? I invert it, and so this is 1 over KW here. And now if I add these up, the sum is going to equal this. And so using Hess's law, I'm going to multiply the K's. And so K for this reaction is equal to Ka for acetic acid times Kb for ammonia divided by Kw. And so that gives me 1.8 times 10 to the minus 5 squared divided by 1.0 times 10 to the minus 14. And so what does this give me? This gives me, let's do that. 1.8 times 10 to the minus 5 squared divided by 1 times 10 to the minus 14. It's going to be 32.4. And so K equals 32.4. And so we were able to figure out the K. Well, that's good, because now what we can do is we can do an ice calculation. And so what I'm going to do here is we're going to take 0.10 molar of acetic acid and 0.10 molar of ammonia. I use 0.10 molar. 0.10 molar is common. We don't like to do 0.10 molar is not that concentrated, right? We don't like to do high concentrations. You know why? We don't like to do high concentrations because at higher concentrations, the errors in our calculation are more significant. Where do the errors come from? The errors come from we're assuming something. Do you know what we're assuming? We're assuming that the stoichiometric concentration is equal to the effective concentration, or the activity. That's what we're assuming. This is why we limit the pH. The pHs range from 0 to 14, 0.1 molar acid to 0.1 molar hydroxide. If we go more concentrated than 0.1 molar acid, we're in the negative pHs. And if we go more concentrated than 0.1 molar base, strong base I'm talking about, we're over 14. Well, what's the problem with going over 0.1 molar? There's no problem with that, because we use 6 molar all the time, even up to 16 molar. But the problem with using 6 molar is 6 molar is the stoichiometric concentration. Do you think the actual concentration of the individual species is going to be? No, because we're going to have ion pairing and all those other interactions occur, and so the calculations are going to be in error. So they kind of restrict it here, because if you start going to higher concentrations, we really should be using activities, not the molar concentrations. And so this is why so many of the problems I use, I'm going to start off with 0.1 molar, because I don't want to go higher, because I'm worried that I don't want too big of an error. And we're already pushing it. We really should be using the activities, but it's okay. And so let's go ahead and do this ice calculation really quick. It's going to give us acetate and ammonium. So I'm just interested in the pH. You know, if I add, you know what, the pH, shouldn't the pH come out to 7? I have equal amounts of acid and base. If I have equal amounts of acid and base, will the pH come out to 7? That is, you know, all the bases can neutralize my acid. So will the pH come out to 7? Well, let's see. You know what the answer is? No. The pH doesn't come out to 7. Why? Well, actually, maybe the pH does come out to 7. In general, the pH does not come out to 7 because the acid and base can have different strengths. But we think, what impact is that going to have? Well, let's see. This is going to be minus X molar, plus X molar, plus X molar. This is going to be 0.10 minus X molar, 0.10 minus X molar, and X molar. And so we'll just go to K here. K is going to equal the acetate times the ammonium divided by the acetic acid and the ammonia. And this should equal 32.4. And so the acetate and ammonium is going to give me X squared, and in the denominator I'm going to have 0.10 minus X squared. The math is easy here. I don't need to use the quadratic. I can just take the square root of both sides, and that will give me X squared over 0.10 minus X is equal to 32. Oops. X, yeah, 32.4. Which gives me X is equal to 3.24 minus 32.4x. So we'll get 33.4x is equal to 3.24. X is equal to, what is it?
The square root of 32.4.
Oh, you're right. Square root of 32.4 is not 32.4. Square root of 32.4 is 180. Is that right? No, that can't be right either. Square root of 32.4, 5.69. So this is equal to 5.69. So let me redo it one more time. This is going to be x is equal to 0.569 minus 5.69x. And so 6.69x is equal to 0.569. X is equal to 0.0850. And so here, I didn't make any assumptions here, so it wasn't that hard to solve. So this is 0.100, let's say minus 0.0850. And so we see 85% reaction. Do you see that? So we're going to be left with 15% unreacted. 1, 5. So 15% reaction, 85% reaction, 15% left over. And so this will be the same 0.015 molar here, and then we'll have 0.085 molar here, 0.085 molar here. So we got 85% reaction. So weak acid and weak base, they don't completely neutralize each other. Do you see there's some unreacted acid and base here? Unreacted. And this is kind of weird because this is going to be a stable mixture of acid and base. Some of it's neutralized, but even the neutralization products, these are acids and bases themselves as well. And so what I want is, I want the pH. What is the pH of this here? How would I calculate the pH of this solution? I need the hydronium concentration to equilibrium. So what are all the hydronium ion contributors? The hydronium ion contributors are going to be in this mixture: acetic acid, ammonium, and water. That'll give me my hydronium, but I also need the hydroxide because I have hydroxide contributors here. The hydroxide would be ammonia, acetate, and water. So what should I do? Should I calculate my total hydronium and then calculate my total hydroxide and subtract the two? Will that work? It doesn't work because of KW. It doesn't work. And so what you do is you struggle. How do I figure out the pH? And then finally, so we don't have that much time, I'm going to talk about it. Oh, maybe I should. How would I figure out the pH? Well, I have a mixture of acids. Remember when I had a mixture of acids, what do I do with a mixture of acids? Well, a mixture of acids, you look for the strongest acid and then work your way down. So let's go ahead with this. The strongest acid I'm going to have present is acetic. The acetic acid is going to produce some hydronium and acetate. And so maybe I'll call that my step 1. And then what's my next strongest acid present? So let's do this as step 1. What's my next strongest acid present? In this mixture? Ammonia? No. Acetate? No. Ammonium? Yes. All right, so I do my ice table here, and then I get down to step 2. Well, step 2, I'll just pick the next strongest acid. The next strongest acid will be ammonium. Ammonium is going to contribute a little bit more hydronium. Okay, and then my step 3, but maybe I don't have to do step 3. Maybe I don't have to do step 2 either. Maybe it's just stop here. And step 3 would be water, Kw. But, you know, I just don't have a mixture of acids, right? I also have a mixture of bases. If I have a mixture of bases, what am I supposed to do with the bases? Well, if I have a mixture of bases, then I better do the KBs to figure out. So I better pick the strongest base. What's the strongest base present? Strongest base present is going to be ammonia. And so I better do ammonia plus water. That's going to give me ammonium and hydroxide. And then, okay, I'll do the ice table there. And then I better go to step 2. Step 2 would be my next strongest base. The next strongest base would be acetate. So let's go with the acetate. That's going to add some more hydroxide. And then I go to step 3, which is Kw. And then what do I do? Well, the first thing I do is I recognize something. Do I really have to do all this? No, do you see something? Can you see something that will help me simplify this some more? What? What do you see that can help me save a little bit of work?
You just want to find the pH, right?
Yeah.
I'll just go with the step 2.
So I just do the acid and just ignore the base. Like the base doesn't exist. We can ignore it. It's not going to have any impact on the solution. Just sweep it under the rug, you know, kind of thing. A little pile of dirt kind of thing. Yes? Can I go ahead and say, okay, base, you know, I know you're there, but I could ignore you because you're making my calculation too difficult. Yeah? No, there's something else. There's something else that, you know, because what I'm seeing is double vision right now. I see double vision, like, you know, there are 2 piles of dust, and I'm trying to sweep up both, but there's actually only 1 pile of dust. Do you see what I'm seeing?
Is it like you can get pH and pOH, and you know that when you add those two together, it's working?
Well, I know I need to do that. So there's something I have to do to keep it self-consistent. In order to do that, it's usually simultaneous. But even before there, you know, what I'm seeing is I see 2 piles of dust, but there's really only 1 pile of dust. I wanted to sweep one of the piles under the rug, but you know, it's not necessary because there's only 1 pile.
You have to conjugate acid.
Yes, all right. If you look at this, take a look at this. This describes the equilibrium between ammonia and ammonium. Didn't we just do that? This is the equilibrium between ammonia and ammonium in terms of hydronium. This is redundant, right? I already did that there. There's something else that's redundant. What is that?
The acetic acid and acid.
Right, this is the equilibrium between acetate and acetic acid in terms of pOH. I have that here. This is acetic acid and acetate. And so there's no difference there. And so I just eliminated a lot of work. And KW's got to be the same for both. And so maybe I don't have to do this, right? And in fact, I don't have to do it because I got lucky because of the conjugates. They're conjugates. And so all I have to do is this. Right? But there's a problem with this. This is not so easy, you know, because this is a weak acid and a weak acid. when we do the stepwise works really well when there's a big jump. Did I already talk about this? When there's a big jump in K's. But here, well, actually, there could be a big jump in K. This might work. This might work okay. Maybe. Maybe not. Well, we could try it. But what turns out to happen in a lot of these problems is we end up having to solve this simultaneously. And so, in general, weak acid, weak base mixture require simultaneous. Except for one type of weak acid, weak base mixture, which we'll talk about. So let's take a break and then we're going to do the lab after that. And I'll talk about the one type of weak acid, weak base mixture, which we're looking at today.